without further ado, I would like to thank and introduce Mr. Ron Creel, who's coming to us this morning and is an expert on space thermal and systems and a systems engineer who has contributed to an amazing host of space engineering projects over the years, including being the thermal control engineer on the Apollo Lunar roving vehicle team, affectionately known as the Moon Buggy. I hope, Ron, I have your permission to use the term of endearment there.
Yes.
And he has come to class today to talk to us about thermal systems and planning for the moon, and has a really amazing set of slides set up. So Ron, thank you so much for your time. We're really lucky to get a chance for all of us, including myself and the students, to get a chance to learn from your work. So thank you, and I'll pass the baton.
Well, thank you, Ariel. I'm very happy to be here today. Give me a thumbs up, hearing me. I always like to see a thumbs up. Good, great. As you can see on the left, that's me a couple of years ago at the Apollo 11 anniversary. They did some projects involving a rover, although we didn't put a rover on the moon until 2 years after Apollo 11. Still, we participated. And I show the Apollo 15 rover here on the right side. My subtitle, my main title is Lunar Roving Adventures, which I continue to have adventures, but I certainly want to stress that you're going to see the subtitle here of Dust Everywhere. Where are we going? What are we going to do? Because that was our main challenge. That remains the main challenge for them. Some realize it, some don't. Okay, I want to show you now a movie. This is the only movie we have of a rover driving on the moon. This is from Apollo 16. We had painted stripes on the chassis side and the wheel hubs, such that we would try to get some information about the relative motion, because we weren't sure before Apollo 15 how well the rover would sink into the soil and how well it would traverse. And you can see here, look at the desolation here. Buzz Aldrin calls it magnificent desolation. Boulders, rocks, craters, the soil that's been beaten up for billions of years, creating this dust. And watch him on the way back as he beats it up, gets more speed. He's having to dodge a lot of craters. And here he comes. This is John Young driving on Apollo 16. Hence, dust everywhere. What are we going to do? We had wanted to do that experiment on Apollo 15. However, the film jammed in the camera, so we didn't get that done. So that's why we did it again on Apollo 16. And they still kept painting the wheel hubs on the other rovers, Apollo 16 and 17. This is my outline. I'm going to go over the lunar module and rover transit and operational thermal environment on the way to the moon. And when you get to the moon, I'm going to also tell you more about the Apollo thermal control system, what we did, about the testing and modeling. Then I'm going to get into two challenges. As I said, the challenge number one is coping with dust. I'm going to talk to you, give you my recommendations about what could be done for mitigating that dust on the moon. Then I'll talk about the challenge number two, which is coping with extreme exposure to extreme temperatures, hot and cold. And I'll talk some about the solutions for those. Then we'll get into a summary and path forward for renewed moon exploration. Now, I understand I'm going to be participating this afternoon in the recitation. And so I pulled a chart out and we'll talk about that later. Going to the moon. Going to the moon, we rode on two wonderful vehicles. The first being the Saturn V rocket. I did get to see 3 Saturn V launches. The last one, Apollo 17 at night, was absolutely amazing. It lit up the sky for everywhere around Cape Kennedy. And then we also, inside the Saturn V rocket, up on the upper stage, above the upper boost stage, the third stage rocket, we had the lunar module and the command and service module, as well as the escape tower. But the lunar module was our carrier for the rover. And you can see here in this picture, this is Dave Scott here trying to review some unfolding. I'll talk about unfolding of the rover. That was a major accomplishment, which was only done and successfully proven a few months before delivery of the first rover. Notice down at the bottom, we had 17 months from contract award to first delivery, 17 months to get the job done and to get everything done to have to integrate in with the lunar module on the right, with magical lunar module. And I'm going to show you now how we went about folding. This was a major accomplishment to be able to fold up the rover and put it inside the lunar module. Had to fold the seats down, fold the back wheels in, forward chassis folded, the aft chassis, then the forward chassis folded, and then some little Teflon sheets were put in to keep the wheels from contacting, from jamming when it unfolded. I'll probably show it again because I think I have time, and I want to show y'all. No, I want you to show you, there are fender extensions on the front and the rear of the wheels. Those are retracted so that the wheels can touch up here, a touching area, or nearly touch. And you'll notice also, I wanted to point out one thing I want to point out again, and I'll get on with that. But I'm thinking about things as I go along here to point out. We had torsion springs in there, which helped in the unfolding, the automatic unfolding. And I'm going to pause it right when I'm going to show the main folding. There's the torsion springs. Those are what you use to bind it up such that it's preloaded. And when it comes out, the astronauts are going to deploy it. And I'll show you deployment coming up a little bit. So that was a major accomplishment. I was up there in a little suburb of Seattle, Washington, Boeing facility. Boeing was the primary contractor. General Motors was the subcontractor, primary subcontractor for the mobility system. And as such, I was up there the very first day that they successfully unfolded the rover. And that was a major, you saw JPL folks applauding. There were a few of us up there of that event, but we certainly were very happy to see that occur and to prove out that you could get the, it's one thing, you can get up to the moon, you got to get it out and got to get it deployed and get it operating. So let's go on to the next chart. Trip to the moon. I think the new moon mission to the moon will be very similar from what I'm understanding, that we'll go into an Earth orbit and check things out, and then you'll boost the upper stage will ignite and you'll be on your way to the moon just like we were for the Apollo missions. And on the way to the moon, we did what's called a barbecuing. For thermal control, you want to balance out the solar energy into your system and the radiation energy that you're radiating away. I want to show you that this is a somewhat sped up video, but it shows you the intent of what their barbecue would be, what we call barbecue. And it's sped up somewhat. I'll show it again because you can see a rover over there. So here's the rover. I want to point out to you one thing. So when it was in the stack on the launch pad, there was a technicians had to go up inside that area, take a door off, go inside, take off this floor panel off the rover, put the batteries in, put the insulation back together, then put the panels back on. That was quite an accomplishment, but you had to do that late in the mission because you're charging the batteries. You want to make sure that they're ready to go when you get ready to leave the Earth. And so there's a rover folded up, and we'll let her barbecue again. I'll tell you that barbecuing generally went good except for Apollo 17. We'll talk about that a little bit later. That's the final mission of Apollo 17. And I've tried to represent here a table over here on the right that shows you our performance. A plot from some friends at Brown University that shows you that for Apollo 12 and 14, they only had 2 EVAs, 2 short walk periods. They were very limited in the traverse distance. But then for Apollo 15, 16, and 17, that's done in the purple, the green, and the blue. So it gives you a relative distance. In fact, what you had on Apollo 17, we went the farthest away from the lunar module. Lunar module is your home base, and that's where you want to know where you are with respect to the lunar module at all times. And I think the same thing is true when you go back up here to the moon again. And I want to point out that on Apollo 15 alone, we did 8 times the distance that you've gone on all 3 of the previous missions. You've gone nearly 28 kilometers. And even Apollo 17 went up to about 36 kilometers total driving distance. This allowed the astronauts to sit, their heart rate went down, their use of consumables went down during that time period that they're driving. It was really a benefit to have the rover there. Also, you could carry more equipment and more samples, as you see here in the samples that returned from the moon. And I think now I want to show you, if I can get this blocky out there, we did that. I want to show you the unfolding. I want to show you the unfolding. The astronauts had some tapes that they released, and then they pulled on these tapes to go through that unfolding where the springs helped to get the rover out. And this is much faster than it actually went, but it's good for these purposes. And we'll do it again. Yep. See the aft chassis folded out. This was a major accomplishment, and a little binding of the saddle assembly. But the astronauts are up there. The rovers weighed 460 pounds each on Earth. They only weighed 77 pounds on the moon. That meant that the astronauts could very easily move things around if things were jammed, to get things loose, to get it onto the moon. Now then, let's go on to the next chart. Let's talk about what we had to deal with was the temperature on the moon. We knew this from calculations and not too many remote measurements, but at least we knew fairly well this temperature spread. The moon has repeating 29.5-day cycles. I asked the question, sometimes ask kids in the class I take, hey, does the moon rotate? A lot of them say no, the moon does not rotate. No, the moon does rotate. It rotates at nearly the same rate as it would take one revolution of rotating to pass one time around the Earth in 1 month. So it does rotate, and that's what you see here, these 29.5-day cycles. So you get solar energy for about half of that, and you're getting eclipse that's shown here for the remainder. I've tried to plot on here. We were there in the lunar morning. I'll talk a little bit more about that. I've shown an overlay here of what's expected for Mars, because Mars is more benign in a lot of ways as far as temperature is concerned. And we were there on the scale on the right. We're planning for missions that go upwards about 250 degrees Fahrenheit down to 30 or 40 surface temperature. Okay, and now let's talk about what we came up with. This is ingenious, I guess, at the time. You got to do the best you can with what you got. And the engineers, us combined with the Boeing engineers and the mobility engineers at General Motors, came up with a philosophy that you've got a vehicle here that's going to have 2 astronauts on it. I'm showing one driver here in this. By the way, these animations were done by a friend of mine in Canada, Don McMillan, and I'm very appreciative of him for what you can do now with computer simulations. We didn't have that level of beautiful that you can do now with the graphics that y'all have for games and such. We did have computers. Some people say that we had slide rules. No, very little use of slide rules. We did have computers. And what you see now, the Rover, it's a 4-wheel vehicle, much like a golf cart with 4 wheels. We call it the spacecraft on wheels. And as such, independent motors and drive systems on each of the 4 wheels, as well as shock absorbers, and an ingenious use of a DC motor with a harmonic drive. A harmonic drive allows you not to have gear shifting. The output is always 1/80th of the speed of the motor is done in that harmonic drive. I'm not going to show you details of that. If you want to, I'll show you. I'm always available at my email down there if y'all need more details on systems like that. And but in this course, we're not going to do that right now. And then the Rover had, as you can see over here on the right, we had a primary constraint of maintaining all surfaces within astronaut touch constraints. They can't be subjected to touching things that are too hot for too long, or sitting down and it gets too hot. And so we had to deal with that. We had to control the display console. I want to show you that now, a video of that, because I'm going to talk about the hand controller, which was there for drive power. You pushed it forward. The hand controller is shown down here. This hand controller. Hand controller was drive forward, drive power, then braking when you pull back on it, and then steering left and right, all done in that one hand controller. In fact, that's the main interface of the astronaut who's driving along for his vibrations. He gets everything fed back through that hand controller. If he gets, hopefully with the shock absorbers and the suspension system, you lessen that effect. I want to show you this. I'll talk to you several things here about, you talk about living on the moon, living on the moon. You're going to need to know where you are, as I told you before. So the astronauts were given this command and control console that allowed them to initialize, power up the system, right? To monitor battery amps and voltages, but monitor motor battery temperatures and drive motor temperatures. Okay. We also had a caution and warning flag, which is shown in that previous, but the caution and warning flag at the top. But certainly, mission control was well aware of what the temperatures were ahead of time to alert the astronauts to that when we did have hot temperatures of the batteries. You'll see on the left side here, information that you need to have is what is your heading with respect? When they started out at the lunar module, getting ready to go out driving, what they did was, as you saw in that video, the astronauts would park down sun, and then he would lift up this little indicator, which cast a shadow on that gauge behind it that gives you the yaw with respect to the sun. I often ask the kids in classes, I said, ask y'all, how did you navigate on the moon? What did you have to give you the net? We didn't have a GPS system, no global positioning system on the moon. And in fact, for the early missions there, they're going to be hard pressed to have much navigation help anyway, without the addition of, they're going to have maybe a gateway someday up there, but that's still only one position and it's fairly far away. We needed to have direct measurement on the moon of our attitude with respect to the sun. So you get yaw there. There's a pitch and roll attitude indicator over here on the side. So he'd get pitch where he was pitch. He'd turn it 90 degrees to get roll. So if you got roll, pitch, and yaw, you've got everything you need to torque up your gyro, to start your gyro up, torque it up, and that tells you what your initial heading is. And then the gyro, what happens with the rover, with each wheel, every time a wheel passed around, it gave 9 pulses into the computer. And the computer then kept track of that and computed, it put a little estimate in there about what slip time. Slip is the amount of time that you're actively engaging with the surface. So, and doing that combined together, that give you an indication of where you were at all times, because you see here, you always want to know what's my distance I've traveled, what's my range to get back to the lunar module, and what's my bearing to get back to the lunar module. Those were all computed and given to the astronauts. And anything else I want to say about this? Certainly, you talk about thermal control. We assume that since the command and display console was up there, pretty good visibility to the moon, that you're going to have dust coverage on it no matter what you did, what you had. So we assumed that we're going to be dust covered. Okay, but we did have a separation of the front panel from the workings inside the meters, isolation there. Okay, let's talk about mobility next. Mobility, as you saw, you had 4 different wheels. By the way, you could have disengaged 3 of the 4 wheels. There was a tool that the astronauts could use to reach in. If a wheel had bound up and a drive motor had stopped working, the astronauts could reach in and disengage upwards of 3. You had to have at least 1 to get you back. It'd be much slower, but you could disengage and free wheel. That was very important. You'll see that very important for y'all as you're designing systems here to have backups on top of backups. And you got to consider what things can go wrong, and sometimes they do go wrong. And what can you do to accomplish that before at the beginning? Now you'll notice also communication. Let's talk about communication. Astronauts had an antenna on their portable life support system. They also had a low gain antenna. It's on this stack here, and you also had what was called the Lunar Communications Relay Unit, which is put on the front, loaded onto the front of the rover. That's the main source of processing the voice communication as well as the TV pictures. Color TV camera. The first color TV camera was put up on Apollo 12. However, the astronaut accidentally pointed at the sun, and we got no color TV images from the moon. We did get our first color images from the moon with this TV camera on Apollo 15. You'll notice it doesn't have a sunshade. We learned, once again, talking about backups, I'll talk about backups. Well, that was something we probably should have thought of ahead of time. We did put sunshades on the Apollo 16 and 17 TV cameras, and it worked better. And then you've got this high gain antenna. That's what the astronaut would, once you stopped at a place, the astronaut would focus it on the Earth. That sent the TV pictures and the communications back to the Earth. Now then, I want to talk primarily a little bit, another couple of charts here on, let me check what time. I'm doing pretty good. We certainly knew that we're going to be dust covered outside. Everything outside is going to be dust covered. Okay. Even if we put all the components in this enclosure up here in the front, this is our forward chassis assembly, where we got an insulated section. I'm going to show you in a minute. But we had 2 batteries and all the drive control electronics and the computer all stored in this forward chassis section in an insulated compartment with 2 dust covers on there, such that when the astronauts got back to the lunar module after driving around, they would open up these dust covers. I'll show you that. And so our radiators could radiate the heat away to space during the time that they went back inside, unloaded the equipment, took their meal, then went to sleep. It's a fitful sleep there, but certainly a cramped sleep inside the lunar module. But they did that. And I wanted to point out that on the moon, we had no telemetry at all going to the moon or once we got there. What we had was the astronauts read out the battery temperatures up here in green, or the traction drive temperatures. Traction drives were very much over-designed. And a movie that I sent to Sean, and y'all can show separately. It takes a little bit longer. I'm not going to show it today, but it shows you how that the mobility systems were much over-designed, and but well able to handle. Maximum temperature on the moon was 275 degrees Fahrenheit for the wheels for the motors on Apollo 17, where we drove further, as I showed you before. The battery temperatures, we'll talk a little bit more about what happened on the batteries, because that certainly was the challenge. And by the way, Ariel, the moon buggy race now is called the Human Exploration Rover Challenge. They got to come up with a new. We got to come up with new acronyms every time. We live in an acronym world, as y'all have probably found out. And hopefully I've spelled out the acronyms in this presentation. So let's move on now. This is our main thermal philosophy, was deal with the dust on the outside, but isolate the electronic components in that forward chassis assembly such that you could deal with that separately. Hopefully. Now, as we said, this is a picture showing the dust covers open, and as you see, it's a battery number 1, it's a battery number 2. The computer under called a signal processing unit, that was our computer, and then the drive control electronics is under this radiator in this section here. And I want to point out a few things. That we only had 10 pounds budget for thermal control, 10 pounds out of that 460 pounds. So what are you going to do with that? Well, the Boeing guys came up with an ingenious system of having strap the energy from the gyro and the computer into the batteries using thermal straps, which are shown, thermal straps, okay, special thermal straps. And then also we found that wasn't quite adequate. So we had to add what's called fusible mass tanks. I actually call them wax boxes. They had literally wax inside. The value of the wax is that while you're storing energy in there, the temperature stays at a constant temperature until you've melted all that wax. So they're like a thermal capacitor. And so we had those in there. I want to point out one other feature here was, if you got back to the lunar module, you opened up the covers and the radiators were real clean, which they rarely were. If radiators were real clean, if you did not come back outside for whatever reason, you want to make sure that the covers closed so that you didn't overcool. So we actually had these bimetallic springs on the side of the batteries to allow the batteries, if they got down to about 50 degrees Fahrenheit, that the covers would close. Only once in Apollo 15 did we have a cover that closed. I'll tell you about that. But I want to show you all what the astronaut, all we were going to ask the astronauts to do to begin with was just to open these covers. So this video shows opening of the covers over the radiators. There you go. There you go. I like these animations. We didn't have the animations back in the day. Well, you can do this now. Little programming. Yeah, y'all like the programming. Okay. Okay. Now then, let's move on. Okay. It was very important to test the vehicle, test the components to make sure that they can operate within their temperature constraints during test program. But the test program also was used to correlate with the thermal models that we built so that you could actually do variations on that, drive longer, drive shorter, do this or that. And the value of thermal models was really great to support mission control. Mission control was very interesting. Mission control, when they ask you a question, it's almost like you better have a very good idea ahead of time of what's the path to getting them an answer as quickly as possible. You got 2 men up there on the moon that are 240,000 miles away, and you better be able to give them some answer if they're going to have to do something a little bit differently or change the procedure around. So we did that thermal modeling. We even put a wheel inside a vacuum chamber on a Lazy Susan with dust in it, flew it on the KC-135 airplane to try to get the 1.6 gravity. And that proved out that we sure didn't need the fenders. I'm glad that we did that test. This picture of me and what we call the mobility over 4, M/4 test. That was taking one of the wheels and motor drive systems, suspending it on above a treadmill, this orange reddish color thing. That's the treadmill, which matched the speed of the wheel and had bump stops on it. All of that put up inside a vacuum chamber. Now remember now, 17 months to do all of what I'm going to show you here. As I've looked back, I'm amazed that we did it. By the way, the Rovers did cost about twice as much as the original budget, but the program manager had that money available. And you learn as you go along and you try to manage costs. but cost is certainly one of your big engineering variables that sometimes you just can't do anything about it. And sometimes you have to take some risks along the way, which well, we tried to minimize the risk. Okay, I wanted to show you this, talk about the wax boxes. This is that previous system you saw with the radio cover, dust covers opened up. And we put that whole system in a tub, we call it the tub thermal vacuum test, and also put that assembly up inside that vacuum chamber also, and tested that, simulating driving periods, and even opened the covers remotely and closed them, and they worked beautifully. With clean radiators, everything worked beautifully during the test. I want to mention other testing. The full up unit, the qualification unit, was a flight-like vehicle, which is now at the Smithsonian. I'll show you a picture of it a little bit later. That vehicle was put in a big vacuum chamber at Boeing, which no longer exists, but it put it up on a 30-degree incline. The vehicle requirement was to climb 30-degree slope. And this test was 30 degrees up, had dynamometers under each wheel to match the wheel speed. All of that inside the vacuum chamber with the sun shining down. And we even put a black coating on, put a black sheet of Tedlar on the top of the console to simulate as if the dust had covered it. And all of that with solar simulator coming from on top. Did that testing, and the system worked beautifully. I'm going to refer in the future to another separate test. After Apollo 16, when we lost a fender extension, I'll tell you about that. We actually took and had an astronaut come in. They have what's called Chamber B in Houston. Chamber B is astronaut qualified, such that we had an astronaut come in and test out a redesign of that retractable fender section. Good luck. Yours here. Okay, now let's talk about the coping with the lunar dust. So I do a time. I'm doing okay. Okay. We had known even from Apollo 12 that their report was that for the short EVAs that were out there, they commented that some type of throwaway overgarment for use on the lunar surface may be necessary. Okay. However, for Apollo 15, we had some engineers at Johnson Space Center actually took Apollo 12 dust, put it in a vacuum chamber, and tested this dust brush. This dust brush was used by the astronauts to clean everything, the TV cameras, their suits, our radiators. So you can see an astronaut up here on the right-hand side actually dusting. Houston people came up with a conclusion based upon their test that, see this lower curve? This is a heat load and the temperature when it's clean. The upper dash plot is when you put 25% dust coverage. Then if you brush it with the dust, you get back nearly to the original solar absorbance. Solar absorbance is the amount of solar energy that you're collecting on the radiator. So we had that test result. We said, oh, well, we're great. We're gonna do great. And even on Apollo 15, the first EVA, we had a good cool down, and I told you one of the covers actually closed. But we started to see, after you opened up the cover the second time, and they got dust on the radiators to try to brush it off, we did not get any cool down on the second cool down on Apollo 15. When we backed out that it was up on the order of a solar absorbance of 0.45. That's 9 times the original value. Then when it got up to, so we didn't have enough time to do much really between Apollo 15 and 16 anyway. And what are you going to do? It looked like, hey, we got by. Temperatures weren't that bad, only about 120 degrees Fahrenheit. Apollo 16 came along, and we were doing not too bad on the first cool down from here down to here, well, down to there. Okay, but unfortunately, commander, he had a hammer in the seat leg, the leg of his suit. They always try to maximize the use of equipment, how to store equipment, and he caught that hammer on the fender extension, popped it off. Well, what this meant was, being the right rear fender extension, it made the lunar dust rooster tail up onto them and cover them. As you can see, pretty bad dust coverage here. Okay, so, but that was fairly late the second EVA. Once again, not much time to do anything. And we got no cool down again after the second EVA. I'm going to show you a little bit later here. I had to put the picture on this chart, but on Apollo 17, when the same thing occurred, the astronauts did do a fender fix using some maps from inside the lunar module. We can talk about that. Okay. Now then, so Apollo 17, we went down to the Cape. They invited us down there to tell us what we'd done. We told them we did a testing. We figured out a new retraction mechanism on guide rails on the fender extension. And we told them, hey, sir, please try to park as far away from the lunar module as you can. They didn't want to do that mainly because the closer you are to the lunar module, it's less distance to travel to take soil samples up or to put equipment off the lunar module onto the rover. But they did that. And in fact, what we saw on Apollo 17 was after that counseling, I don't want to read what, I can't get rid of that blockage there, but essentially read what Gene Cernan said. It's the biggest inhibitor he thought for normal operation on the moon. As I said, unfortunately, Commander Cernan did knock off the cover. He felt really bad about it. Luckily, it happened, as you can see in the plot down here on the left, on the bottom. If I can move the screen, block it. Okay, we were able to. We knocked it off during before the first EVA. Okay, got some cool down. Anyway, he did a much better job of cleaning off the covers before he opened them. And then John Young was the backup crew. Apollo 16 crew was the backup crew for the Apollo 17. So John Young went back in the vacuum chamber and tested and took some lunar module maps and did a fender repair that I showed you previously. That was early enough that we could do this repair on the moon. And then we got modest cool down on the second cool down period, modest cool down. Still not the ideal. I want to point out here on this plot, this is the thermal model for which I received the Silver Snoopy Award after Apollo 16. And we found that the big thermal model was cumbersome. It could not be reset and used for thermal predictions during the missions. It wasn't real-time responsive. So I developed a simpler model of just that forward chassis assembly and those components. And we used that in Apollo 16 and 17. And you can see how good we got it. This is what Mission Control wants to see. When they ask a question about what's going to happen in the future here, they want to know what's going to happen, such that if you follow this plot of this curve up here, what I'm showing there, and go, if you stayed and not opened up the covers, this is where we opened the covers on Apollo 17, we would have exceeded the upper limit midway during the EVA. So we proved to them that, hey, and they approved it to go an alternate procedure to open up the covers during EVA, and we got some cool down. And we finally, we almost wanted to open the covers a little bit later, but they said no. We had 2 batteries, had total backup, so we'll be able to operate and go higher up to the maximum survival limit on the batteries. I want to say that after the missions, we sat there, my thermal mentor, myself, Hugh Campbell, my senior thermal mentor, myself, we sat there kind of wiping the sweat off our brow and saying, hey, gosh, the astronauts spent too much time doing housekeeping on the moon. We should not have made them do that. We really regretted that. And I'm not going to show this movie here, but I've included in the package that Sean has that y'all can look at the astronauts, about a 2-minute movie showing them trying to clean off dust using that dust brush. It was very frustrating there. And as such, it's also a health hazard if you get that dust back inside the lunar module. And I've done a calculation here based upon the amount of money spent to send astronauts to the moon on the Apollo program. That 2 minutes is equal to $82 million. At the time, $82 million spent housekeeping. And that's not what you want to be doing. Okay. So what I have seriously advised NASA folks about, people about, is let's learn from our past experiences. Why deal with the dust at all if you don't have a good solution? And I don't believe they will ever come up with a good solution for trying to clean it off. And it's a health hazard for the astronauts. Let's focus on isolating the astronauts for the dust exposure. When I went out to Houston, I was invited out there in 2007. I was very pleased to see that they had already developed what's called the Chariot rover. And by the way, this same vehicle was in the 2008 inaugural parade for President Obama. And you see how you can leave the suits outside. You have suit ports, you can leave the suits outside. And I'll summarize this, that not only had done that, NASA had also done a tremendous amount of work on the what's called the Z2 suit, and a suit that you can climb into and climb out of, as well as even having dust covers, studied dust covers, and use of airlocks. Unfortunately, I don't see them trying to go that route nowadays. I think it's a big mistake. We may suffer that in the future, but this would require extra mass to do this, to do a vehicle like this. But you can do certain things with the suits and with airlocks, with the systems that you have control over already. And I would like to summarize what I've told them is Earth-based loose dust environment simulation and testing is very difficult and not reliable. Isolation from lunar dust is required for successful future moon crew operations. I sincerely believe that. Okay, let's talk about the hot and cold temperatures quickly. This plot here shows you temperature, calculate that, these equations down here for latitude and altitude, sun elevation angle. And about this Apollo 16, where we would, hottest temperature we had was about 200 degrees surface temperature. The Russians, we were there in the morning period, so we didn't endure the lunar noon. The Russians and the Chinese have both found that you've got to turn off vehicles, not try to operate when the sun is up there near its zenith. And Russians, it was about 2 days before and 2 days afterwards that they couldn't operate, primarily because of everything is washed out. You don't have trees, you don't have any roadway. So everything is washed out due to the sun bouncing off. Quickly over there. Now, I want to stress back there. That's 14.75 days of solar heating each cycle. Okay. Systems like I showed you, that Chariot can help you with protection against the noon time period also that you've got. It's called a multi-mission exploration vehicle. And as such, that can help you. But going back to your lunar module can help. Of course, I don't fully understand how you want to limit yourself to just being around the lunar module. I think you want to get out and explore great distances. So you need to have vehicles like this with a closed up container with the suit ports in the back. That's what I propose. Okay. For the cold, just as you had nearly 15 days of sun, you've also got nearly 15 days of no sun. And as we can read what's stated here, present time, the missions are only planned for about 7 or 8 days on the sunlit side. They're going to have to leave the moon, go back up into orbit, and not try to endure on the moon. Ways that you can get around this is if you pay attention to what was done in the past. All of the Apollo lunar surface experiment packages that were left on the moon, all 5 of them, had SNAP 27 radioisotope thermoelectric generators. You can see dust on there. It's hard to keep dust off of anything up there on the moon, kick it around. And those were operating for several years until they were shut off in 1977. Why were they shut off? Budget, money. Unfortunate. We've had no data from those systems since 1977. That's unfortunate, but true. Other systems that have successfully used isotope heater systems, where the Russian Lunar, which actually landed before we got our rovers on the moon, they landed in November 1970. They used an isotope heater on the outside. They passed a gas by that heating system and survived on the moon. And you see the relative size difference. The U2s, the little rabbits that the Chinese have put up there, the first one didn't survive the first lunar night cycle, but the one on the far side has survived and is operating. These systems, all 3 systems, use nuclear energy. What caused Lunar 1 lasted for 11 months, and Lunar 2 only lasted for 4 months. When I was in Russia, I finally got to get the fellow that drove their rovers on the moon, to tell me why did the second rover only last 4 months. It was because if you look at this cover here, they went down into a crater that was too deep. They panicked. They started driving back up, and the solar panel was open, and it caught lunar soil on the side of the crater. That dust later on, when they closed it up, it got on the radiator, caused overheating. So a thermal problem there. Okay. The summary, I'll summarize for y'all. I think I'm doing pretty well. Not too bad. I believe that there are challenges, like you said, to go for both lunar dust and day and nighttime survival. Challenge 1, I've told you, we need isolation. Challenge 2, for lunar daytime stays, we've got to do something about the hot temperature at the lunar noon. The longest success for survival in the lunar night was using nuclear systems. Thermal vacuum testing with using thermal modeling is vital for moon exploration. I have tried recently to get NASA interested even in going back, pulling the qualification unit out of the Smithsonian, and even LRV number 4. There were 4 rovers built. There was an Apollo 18. Don't let anybody tell you it wasn't. We were looking at taking and putting a trailer on the back end of the rover after Apollo 18, and then driving it around on the moon. This number 4 unit is down at Kennedy Space Center. I've tried to get them interested in that. They don't seem to be interested, but that's life. Finally, you asked Ariel, you asked before, what do I do? I'd help out Space and Rocket Center. We built a replica for the here I am sitting on the replica. And I do take my simulation, which has the full thermal model in it, around to schools, and kids can drive it. That's the advantage of you're driving games now. And I don't know, how are we doing on time? Should I try to show this other video or not? It's not too long.
I think we should probably stop here just so you have time to take maybe one question
good
from
questions.
the group. Yeah, because we want to make sure we get time for our next speaker as well. But Ron, this is an amazing amount of information. Thank you so much for condensing it into a very short time for us. We really appreciate that. And to all of the students in the class, I would say the session has been recorded. You should go back at your leisure and watch back through this video for all of the incredible details that Ron has pointed us to. Ron, if you want to close, and then I'll give a chance, maybe just one question from the students. And if you have other questions for Ron, you can put them in the Zoom chat.
Right. As you saw, I let my TV camera control around here. This is ground controlled television assembly, ground controlled television assembly. And he's looking for a question. There's a question. You have a question?
Do we have a question from the group here? I'm on my...
Ariel, could I ask a question? This is Jeff, and then we'll see if a student does. But Ron, hi. There's lots of lunar dust simulator that we have here on Earth. My understanding, it's mostly a chemical simulation of lunar dust. Do we have anything, when you do all those tests, how do you simulate the fractal nature of lunar dust using material that we have here on Earth?
It's very difficult. I tell people, you've got two things working against you. You got the 1/6 gravity, okay, but you've also got extremely low pressures. The best you could do in thermal vacuum chambers here on the Earth, about 10 to the -9 torr. We got that on a few tests, but that's without soil in there, okay. On the moon, it's 10 to the -14 torr. You can never simulate that. So yes, you could try with simulants, but they talk about electrostatic buildup and whether or not you use a wand. I don't know what you can do with that wand after you clean off the suit. What are you gonna do with the dust that's on that wand? And then you're still gonna carry back the lunar soil into the habitat, which I don't want you to be doing. I want you to leave the suits outside. For exploration of Antarctica, we leave the suits outside. They go outside, they explore around, they come back, they call it what's called a mud route. They leave the suits outside of the living area. And I think that's the key element, but I don't seem to hear a lot of people hearing me.
Vaishi, would you like to ask your question, and then we'll transition to our next speaker?
Thank you, Ariel. And thank you, Ron. That was just what a great talk it was. And I'm going to watch it again just because there was so much information. My question was about how you designed for battery management on the rover, and how did you monitor the energy storage capacity? How did the astronauts monitor it? Because you didn't want to leave them stranded. It seems like a really important design problem.
That's a very good question. We had the monitoring. They could monitor the amount of available, the amp hours still available. We started out with 242 amp hours available. Each and every mission only used about a third of that energy. So we certainly were much over designed, but that's how it was monitored. Was they read out to Houston and say, hey, here's your amp hours versus time. With the people, the battery people then would plot that up and say, are we on a rate? Are we on a rate that's a good rate that leaves enough energy available at the end of the EVA? Now, we did have to turn off a battery on Apollo 16 because it was getting too hot, and because of that dust getting on the radiators and not being able to clean it off. And so we operated. Oh, I didn't tell you all the other thing. On Apollo 16, we got real ambitious. The people in Houston, they had 3 different wax boxes in their Lunar Communication Unit up here on the front end. Okay. But they also had a battery that they had to replace. So since we only use about a third of the energy on Apollo 15, they said, hey, why can't we power all the communications units off the batteries from the rover? So we took that extra burden on of even more power being used to accomplish the communication. We had to back off on that on Apollo 17 somewhat.
Ron, thank you so much for the great answers to the questions, and for, again, just an incredibly informative talk. We really appreciate your time. If you're able to stay, you're more than welcome. So we won't kick you off. I don't know if you have other plans for the morning, but you're more than welcome to stay for the rest of class. So if a class can just thank you so much, Ron, for your time. And now we will switch over to our next guest speaker.